Today, we're going to pull back the curtain on the math behind some of the most high-stakes decisions happening all around us. It's a simple yes or no classifier that, believe it or not, runs millions of times a second. And it's shaping everything from your email inbox to, seriously, life or death situations in medicine and engineering.
So let's dive right in. I mean, think about it. Every single day, you're dealing with systems that have to make a choice between just two options. Is this email spam? Did that part coming off the assembly line pass quality control? Is a user actually going to click on this ad? Our world is absolutely filled with these simple, binary questions.
So the big challenge, right, is how do we teach a machine to make these calls reliably? Let's say you've got data on a bunch of students, how many hours they studied and whether they passed or failed an exam. What's the first tool you'd probably reach for to try and find a pattern in that data? Well, your first instinct, and it's a good one, might be linear regression. It's a fantastic tool. It's great for predicting a continuous number, like using a house's square footage to guess its price. The logic is so simple. Just draw the best possible straight line right through your data points.
But here's where it all falls apart. When you try to force that straight line onto a yes-no outcome, which, we code as 1 for yes and 0 for no, that line just doesn't know when to stop. It'll keep on going and can predict values like 1.3 or even negative 0.3. I mean, what does a 130% chance of passing even mean? It's mathematical nonsense for this type of problem.
So here's the fundamental mismatch, right here on the screen. Linear regression is built to predict something along an infinite line, but our problem only has two answers. What we really need is an output that acts like a probability. A clean, sensible number that stays between 0 and 1.
And this brings us to the aha moment, the truly elegant solution, logistic regression. Now, don't let the name fool you. Despite having regression in its name, it is an absolute master of classification. Its whole job is to take that runaway straight line and just gently bend it into a curve that respects the rules of probability.
The secret weapon here, the key to this whole thing, is something called the sigmoid function, and it's this beautiful S-shaped curve. It's basically a mathematical transformation that can take any number you throw at it, positive, negative, huge, tiny, doesn't matter, and it squishes it into that perfect range between 0 and 1. Now, from an architect's point of view, this isn't just some random curve. Oh no, it's specifically shaped to translate that raw output from the linear model into a probability that actually means something. This thing is our probability machine.
So the whole process becomes wonderfully simple. You've got two steps. First, the model calculates a score, just like our old friend linear regression would. Then, and this is the magic part, it feeds that score, whatever it is, into our sigmoid squisher function. And voila! The result is no longer nonsense. It's a meaningful probability, like 0.69, which we can look at and say, okay, that's a 69% chance.
Okay, so this is great. The model now gives us a probability. It might say there's a 69% chance this email is spam, or maybe a 30% chance a student will pass. That's super useful information, but it's not a final decision, is it? We still need a definite yes or no. So how does the machine make that final call? It all comes down to a simple but incredibly powerful rule called a decision threshold. You can think of it like a line in the sand. And by default, that line is almost always drawn right smack in the middle, at 0.5, which represents a 50% probability. And the rule couldn't be more straightforward. If the probability it calculates is 0.5 or higher, the model slaps a 1 on it. It's spam. The patient has the disease, the student passes. If it's anything less than 0.5, it gets classified as a 0. It's this simple threshold that turns a kind of fuzzy probability into a clear, actionable decision. Now, this elegant mathematical trick, this logistic regression, it isn't just for sorting your emails. It is the quiet, unseen workhorse behind some of the most critical decisions being made all over the world every single day. In one of the most tragic and famous examples, after the Space Shuttle Challenger disaster, analysts went back and they found that a logistic regression model, just by looking at past data on temperature and O-ring failures, would have predicted an extremely high probability of catastrophic failure on that freezing launch day. It's an unbelievably powerful warning system. And think about this. In intensive care units, doctors use models that take a patient's vital signs and calculate a probability of mortality. Now, this doesn't replace a doctor's judgment, of course not, but it helps them rapidly identify and prioritize the patients who are at the highest risk, and that can and does save lives.
Oh, and every single time you apply for a credit card or a loan, a model just like this one is humming away in the background. It takes your financial data and calculates the probability that you will default. That one number is a huge factor in whether you get approved or not.
Seriously, the applications are just everywhere, often in places you would never expect. This classifier is predicting if a factory part is about to fail based on vibration data, if a person is a likely voter based on their demographics, and it's even helping sports teams predict the multi-million-dollar probability of an athlete becoming a star.
So what's the big takeaway here? Ultimately, by understanding this simple two-step process, that linear calculation followed by the sigmoid squish, you've basically just grasped the fundamental concept of a single neuron. This simple classifier is the foundational building block for the massive, complex neural networks that powers so much of modern AI. Honestly, it's the very first concept I make sure every new AI architect understands inside and out. Which, leaves us with a final, pretty provocative thought. We've just seen the incredible predictive power of just one of these classifiers. So what happens when you stop thinking about just one and start thinking about what's possible when you connect thousands or even millions of them together? Well, that's where modern AI really begins.